Welcome everybody to BioGears presentation of our build system. Just wanted to really quickly give you an idea of some of the resources that are available to you in BioGears. So first off is our website where you can click on our documentation and see details of any system. Also our GitHub page. Please don't use Engine, it's deprecated. Clone Core, this is where all our current development is happening these days. And also, if you want a more detailed overview of BioGears, please reference this video. It is the most up-to-date video on BioGears on YouTube. It was given to an SSH affinity group. So thank you. Now I'm going to hand it over to Stephen for build instructions on the Windows and Linux architectures.
Okay, so today we're going to go over building BioGears from scratch on both Windows and Ubuntu using our new cmake-based build system. Our previous build system leveraged a technology called Ant, which was primarily designed to build Java components, and then to make that system as complicated as possible, it required cmake to build C++. So you ended up needing at least 3 build architectures before you could get an executable, and we hope that this will be a little bit more straightforward and require less predetermined paths for where you stick all of your dependencies. So all of the documentation that I go over today is already on the wiki on the core repository. So if you scroll down, we have building from source, and we go over the dependencies that BioGears has, a very basic utilization of variables that you can change the behavior of cmake with, and then we have a list of architectures that we currently do our continuous integration testing for the current BioGears release. So this first talk is going to be focusing on Visual Studio 2017, and we're going to build a 64-bit build, which is new to the BioGears 7 release. Previous releases were limited to 32-bit binaries. You can download any edition of Visual Studios to build. We include a link to the community edition, which is free for non-commercial use. And then we do require that the version of cmake that you have installed for all platforms be at least 3.12. The link in the wiki goes to a release candidate, but it's officially released now. Certain parts of the configuration will fail to properly go through if you use 3.11 or prior. So on this VM, I already have the Visual Studios edition installed, and then I have cmake as well. And a lot of the configuration that we'll be going through is going to be based off of just using the command line, but you could do this graphically with the cmake UI as well, and I'll demonstrate that towards the end of the presentation. So the first step, since this is a clean install and it doesn't have any of the dependencies, is just to download each one of the zip files that's listed in our dependency list. So we'll go ahead and get that started. And then once everything's downloading, I like to stick them in a common folder that just keeps track of where everything is. So in this case, to speed things up a little bit, we already have them downloaded in addition to the place that we did here in C:\source. And most of the documentation assumes this location, but you could put anything, put all of these dependencies where you'd like. So I'm just going to uncompress them very quickly, and then we'll walk through building all of the dependencies and storing them in a common location. So the first dependency that we're going to install is Eigen, and Eigen is a templated linear algebra library that we use for most of our numeric solutions inside of BioGears. Because it's header only, you really could copy and paste the headers into your sysroot structure that we're about to make, but cmake simplifies that by allowing you to just go through the process as though it did build binaries. The problem is that its cmake configuration step takes a little bit longer than most other configuration steps. So I'm going to demonstrate this really quickly, but I already have it installed so that I don't have to wait a lengthy period during this presentation for Eigen to finish. So anytime that you're using cmake to build anything, you always want to create an out-of-source build folder. I typically, ironically, make that build folder inside of the source directory just by making a directory named build, and then running cmake from inside that. So you'll see all of our commands lead off with the 2 dots relative to say that the source code is one directory up from where we're at, and then they hand off the -G flag, which specifies which actual compiler you want to use. So in this case, Visual Studio 2015, 2017 Windows 64. The next flag we give is an install prefix, and that just tells this tool what folder on the file system we want it to install once it's been built. We're going to copy that into place from this directory, and as you can tell, it takes a good while for it to search for all of Eigen's dependencies and decide what it has to do. So we're going to let that run in the background, and in the meantime, I'm going to start on the next dependency. So you'll notice that most of the commands are very similar when building the dependencies. We're just making sure that they all install into the same place. And if you be patient, this will just take a second to configure, and then we'll get to building and installing it. Just as a comparison, how long I can take.
So obviously, the instructions include, after the release configuration, a debug configuration. Would I want to run through both of those?
So that depends on how you're going to use BioGears. So for these instructions and today, I am going to go ahead and build both the release and debug configurations for each of the dependencies because other than the Eigen configuration step, they're fairly quick. But if you were just going to use BioGears for like research purposes to run simulations, you would want to stay away from the debug builds because they are prohibitively slow and really should only be used for tracking down bugs once you've identified a way to repeat them in release. BioGears typically runs somewhere between an 8-to-1 to 10-to-1 ratio depending on your modern processor. In debug, it can run almost the inverse of that. So it will take 10 seconds of wall clock time to simulate 1 second of debug simulation time instead of the inverse, which is we normally simulate about 10 seconds of simulation time for every 1 second wall clock time. And any time I'm stopping to build any of these sections, the WebEx is interactive, so if we have questions, feel free to ask them. Now that we have log installed, I'm going to go ahead and build Xerxes. Log for CBP is just a generic library for multi-platform logging that we use, and Xerxes-C is an XML parsing library that we use for all of our CDM. And Eigen's still not done, for entertainment purposes. So to save us some time of just demonstrating its pause, it is normal for it to take that long on a new machine. You now would just type cmake build install, and it would place everything in position. I can give that demonstration. It's not going to hurt anything. And then you would finish. Now, while that's going on, Xerxes is probably the lengthiest compile of our dependencies, but it's still fairly quick. Where we're installing these is currently in c:\BioGears, and I'm placing them in external so that they just create like a grouping in a common layout that you'd find on a Unix system of all of the DLLs, the linker libraries, and the include header files in one folder structure. The Windows developers tend to like to keep their externals separated, each in a separate folder structure that duplicates these kind of common files. And that's fine, cmake can handle that. You would just give it a longer cmake prefix path. But I would like to keep those commands shorter for this demonstration, so instead I'm installing all the dependencies the same. There are trade-offs for both builds. It's easier to set up compile chains when they're consolidated, but it's harder to verify that you've uninstalled and upgraded a dependency when they're consolidated, and that's much easier when they're separated. You can see we have Eigen, we ran that, we have log for CPP. Next we'll get Xerxes, and then the final dependency that we have is XSD code synthesis, which has an open source license for use in open source projects and is a XSD to C++ code generator. So all of our CDM definitions are stored in the BioGears source base as XML schema definition files, and the XSD compiler parses those files and generates C++ code, which we then compile to create all of our parsing objects and interact with them inside of the code base. So it itself uses Xerxes as a dependency in that code base to actually do all the serialization when it reads in a file. But both of those are required for the CDM. So the hopes and the goals with changing the system, for anybody who is familiar with the old system, is just to make sure that BioGears compiles exactly the same as all of its dependencies do, and to simplify the lift of moving between the various open source projects so that they have a common pace. So when we get to compiling BioGears, the steps to compile it will be very similar to all of these dependencies. It's just that we have one additional variable we need to pass cmake, which is the location of each one of these dependencies so that it can search for them and auto-configure. In the previous build system for Ant, those were just typed into a text file. So each user was expected to open that text file and physically alter it themselves and run it. And that could get very complicated because there were a lot of assumptions made into it. And so we've removed those assumptions, and that should hopefully make everything a little bit more transparent. It's easier to cross-compile the system now in case you need to target like an ARM architecture, but you develop on like an Intel Windows build. And it will hopefully allow us to more seamlessly support platforms that we can't immediately integrate into our continuous integration testing as a team. Well, while we're waiting for this, since it's taken a little bit longer than I remember, I'm going to go ahead and get a start on cloning the new repo for BioGears. So I'm going to open up a second command line, and I will move this one over and build it in parallel. It just finished. Go ahead and start that. And then we will scroll down just a little further, and we will clone the core repo. So the main reason for the change is just so that we can think of the results of the core window as being libBioGears, which can be used as an integration tool for other projects. And then our external repo UI, which Austin showed us earlier today, will be one of the first projects to use that and treat it completely as BioGears as an external dependency, much the way that we're talking today. About using Xerxes and XSD as external dependencies. So we do not have a functional version of it working now. We're finishing up a couple of workloads and we're starting to prioritize this. But in the next couple months and hopefully in the next 2 quarters, we hope to have a fully functional Qt-based UI, which we can release in binary releases and have an installer so that anybody can test the functionality and test out everything that BioGears can do. And as always, everything that we do since the switch to 7.0 is developed live, so you can actually interact with us with bug requests, you can see commits that we're doing on other branches, and eventually we'll have stable releases that are available so that if you need to depend on a build that happened, you're not dependent on new features being introduced into master, maybe changing minor variations inside of the output results.
And we will support a legacy, what's called a toolkit on our BioGearsEngine.com website. That will be the last release of our Java-based, what we call a toolkit, but it is a user interface for using BioGears. We will have new zips up there for BioGears 7.0, which is what we're calling the new patch to cmake. So once we update our website, those new zips should be up within the next month or 2. And we will send out, and there will be, you know, a news release of that release, and then all of the zips will still be there. And as we tag new releases in GitHub, we will also provide those zips on the website. And then also those zips will be included on the GitHub page as well. So if you'd like to just download a zip and start from one release, you can still do that.
So then the next dependency that we're going to build is a Windows-only dependency. It's a header called diren.h, which is traditionally a Linux system header. So this basically ports the API functions that are available through that system header on Linux to Windows. We maintain a clone of the repo from the developer that used this, but we only modified the installation for that clone. So a different team actually supports it, but it's fairly stable and we don't expect to see many patch changes from it. And as it's simply a simple header, we're really just using cmake to follow that nice installation logic that we see in all of the other projects. Can't copy it all. Just to make it a little bit simpler and more intuitive to the user. One thing I would like to point out, in all of our instructions, I break the install and compile steps into 2 separate commands. And I do that so that I can look for bugs before cmake would install any files or anything. But you can skip the non-target install steps if you trust that everything's going to build correctly, as it will detect that building is a requirement for install to finish. So I'm just going to demonstrate that very quickly. And so that copied .h into place. The last dependency that we have, we're actually going to use a graphical tool for, and that's XSD. We're going to go into source, and we're going to go into XSD. We need 2 pieces of XSD. Now, you could point, we've upgraded our build system that if you pointed the cmake prefix path just to this directory in addition to external, XSD would be detected automatically. But just so that we can keep with this mindset of having everything consolidated, I'm going to copy the XSD compiler, which is self-contained, into BioGears external bin. And then I'm going to copy the XSD required includes from libxsd into BioGears external includes. With that done, we have now built all of the dependencies that we need, and they're in a consolidated place. And we are still waiting for the clone to compile or download. Taking much longer than expected.
So you can copy the XSD information into bin and include, but you can also configure that through the cmake.
Yeah.
GUI or modify the list file.
So the way that would work is cmake has a list of paths that it automatically searches for certain things. And inside of its install, it knows how to find several dependencies. When those dependencies don't include things that we need, we add search files. But if you look at the build instruction list, we go over this really special variable, which is the cmake prefix path. And this variable preempts the pre-known path.
It's cloning pretty slowly.
Yes, I agree. I might download it as a zip file in a second just to show that as an alternative version. So this variable can be set to a semicolon delimited list of places to search. And so if you wanted to, we could easily have made this value basically cmake prefix path equals, we're going to do this one already, BioGears external, but you could also then do :/src_xsd. And that is just the directory which I extracted XSD to. We have taught our build system to look at just an unzipped release of XSD and to automatically find the headers in libxsd and to find the bin in bin. But if you go ahead and install them in a traditional path, so they're in include, it would also find them there. So you have a little bit of leeway in the way that this works. On other systems, as we'll show in a little bit on Linux, you have basically the ability to download a Debian package and have it install on your system just naturally, and so that would also be an alternative. Other variables inside of the system are the install prefix, which we've been setting for each one of the dependencies. That decides where BioGears is going to install all of its files, or for any other project, where the files that get built plus the headers need to install at the end of it. We have several flags that relate only to this project, but we have the ability to toggle off certain pieces that we are building. And for most of these instructions, we do choose not to build the Java tools. But we also have a series of executables which take some time to build. And so if you want to skip that and you're just interested in the scenario driver and the libBioGears library, you could turn them off. It speeds up, you know, maybe 3 or 4 minutes off of the build. So if you're doing a lot of rebuilding, that can be useful. The other variable that's important, and this is a more advanced feature, but this cmake root find path is used to set where if you were cross-compiling and you have another processor architecture that you're targeting, the cmake root find path is where you set the location of all of that other architectures includes, and the prefix path would be where you set your current host or the machine that you're using to compile includes. And where that's important is I said that we depend on the XSD compiler. You have to be able to execute that. So you would stick the path to the XSD compiler in the cmake prefix path, and you would stick the path to, say, in this case, the ARM64 headers inside of the root find path. And if you look at the documentation for the ARM HF or the AAR64 builds, they have examples of all of this. And since we're still at 45% and GitHub seems to be throttling us, I'm going to attempt to give a different demonstration of how to use the code, which is to download a zip file over HTTPS. Yep, thank you very much for that. So when you do a git clone, you get a lot of our metadata with it, because I chose not to do a shallow clone so that you can also commit to the project and be a developer. When you choose to download a zip like this, that can't be right. It only gives you the source file, and so it's a much smaller download. It also, right now, is going at 2.8 megabits a second instead of kilobytes, which is interesting.
I don't know what's up with that clone.
So we'll just go ahead and stop this, because the clone is definitely going to be faster at this point. And in just a few seconds, we'll continue on with the demonstration as though the clone had worked out.
Also, if you've come in late, all of this is being recorded, and we will be pushing this up to our YouTube page and then sending out links to anybody who's interested. So please just, we'll send out our mailing list for updates on that. Also, if you're interested in a direct WAV file of the presentation, please contact me or Stephen. We'll give you our contact info at the end of this presentation, so you can reach out to us. Also, feel free to ask questions anytime. If you came in late and you missed something, we're always happy to kind of back up a little bit if something seems like it's missing.
So now we'll just extract that zip, which internally has every file that would be in the git clone. You just lose the ability to actually view the git history. So this is probably the fastest way to get it if you're just looking for a quick way to do a build.
And so we've handled all the dependencies now, right? So we're just going to be building BioGears.
That is correct. So again, we're just following the instructions, and we're just going to run this config line, which is a little longer than the previous. So it's got the install prefix, it's got the prefix path to external. And then for right now, I'm going to turn off the how-tos and the Java tools, which I talked about earlier. Not work yet. So you can tell from the error message that I forgot to make my build directory, and then since the command says the source code is one directory up, it wasn't, and that's why it says the ccolon / isn't a source directory. So cmake is good at also finding errors for you when you mess things up. So our configuration doesn't take too much time. I am on a virtual machine so that we can show this in a repeatable context of doing this fresh. Mostly the beginning is just auto-detecting where things are. We look for Java. Then we do this XSD generation step where we generate all of the CMD headers. And after that, it will recursively look through all of the files where we store and give you output for that, which is mostly for the development team just to make sure that a file is found if it's missing from the guide. Once this is another way that this could have been done to be more friendly, I said that I would show the GUI. When you install cmake on Windows, you also get access to this tool, which is just the cmake GDK GUI. And if you look at it, and you were to go into build binaries and core master and then come to the build folder, it will give you a list of all the variables that it populated. I normally keep group checked at all times. For various reasons, you might need to toggle advanced on and off if you're looking for something, because normally if we find all of the libraries, we mark them as advanced so that they don't clutter up everything that you're looking for. And so in here, if you did want to turn on the how-tos, you would just simply check them and then click configure and generate. And what's nice about this UI is it has an open project button. So after all of that's done, it will automatically open Visual Studios for us.
It's giving us a message here about the Java tools, and that's because Java is not installed on this virtual machine.
That is correct. So it does automatically check for them. It would build them by default if it was there. And it's just warning you that one of the commands to generate like pre-stabilized patients isn't available unless you have the Java tools. We'll be working on that in a future release. So right now I'm just logging in with my Microsoft account to get the graphical version of Visual Studios available. We've been using the command line tools without the requirement of this, but just to get into the IDE, it's a new feature for 2017. And this will pop up in just a second, and I'll walk through kind of all of the targets we have and what they do, and then I'm going to shut down this VM, and I'm going to open up a VM where BioGears is already built, because it's a significantly long compilation time on like a modern i7. It can take up to 30 minutes or more to build BioGears from scratch due to a lot of inline coding and optimizations that we have. So the layout that we have when things first start is basically we've got the binaries folder, which would be like in the final versions of executables that you would run. So inside of it is the scenario driver, which is an executable designed to run XML-based scenarios that include a patient and an environment and then like a timeline of events from beginning to end, and then show you the results in a command line. And the test driver is a development utility for running unit tests that basically simulate subsections of BioGears and just make sure that they are mathematically converging as we expect. The core part of BioGears is in this library section, which is the CDM library and libbiogears. If you are a BioGears integrator, this is all you need to build, libbiogears, and then your project needs to link against these three libraries. And of course, you need access to the headers, which are included into the install. The how-tos that I mentioned earlier, since we checked to build them, they're listed here. They are just examples of how to use BioGears as an SDK, as an integrator. Each one of them has a few source files. They have a main, which simply calls one function. This is common across all of our official how-tos. And then the other files include all of the actual code for how to load a specific patient, generate an engine with a log, and then run through and probe BioGears for all of the data that would happen. So, you know, just as we create different actions, we tend to write a how-to that just demonstrates how to use that. And you can scroll through the source code for each one of these and just see different ways that we develop and experiment with BioGears. The other thing I would like to point out is the code generation segment. These two generation steps are what generate the XSD code. They normally, if you're not modifying XSDs, they only need to be run the first time you ever compile BioGears. If you do choose to modify an XSD file, which we can talk about at the end of this presentation, then you would need to rerun schema data model first, followed by BioGears data model. And then that's going to cause you to recompile BioGears all the way through, and when that's finished, you could test your changes. So with that going, everything's compiled. I'll demonstrate just what the start of a build looks like, and then we're going to stop the build and open up a different VM. But we can see in this output all of the files being generated. And then every once in a while, I'm going to stop, well, let's stop the build. We see these generating lines. They happen the first time you run. That stages all of our files that we keep in shares so that we have in version control as they move into one location in runtime, so that all the dependency files, the XSD definitions, the scenario definitions, and any of our logger configuration are available to the executables in the binary for running. And so as an integrator, if you were going to use BioGears, you could generate that file by using just right-clicking and building stage runtime. And once it's done, you could copy that into your integration space, and the lib BioGears would be able to run simulation. So let's go ahead and switch VMs. It'll only take a moment.
And so on this VM, just imagine that you click the build button through BioGears, everything completed successfully, and now we have our pre-built libraries already generated. Because that step takes long and we don't want this to be a 5-hour, well, really like a 2-hour instead of a 1-hour, we decided to have a pre-built VM just so we can demonstrate a little bit of how to run scenarios, of how to interact with the how-tos, how to run them as well. So, yeah, just to give you an idea of use cases as well. And then the Linux build, we're going to get up to that build step. But so if you want to know details of how to run things in Linux, you can obviously point the executables to the appropriate XML to have Linux run those scenarios. If you don't have a IDE like Visual Studio in your Linux environment, you should, after the build step, still be able to run all these things. You're just going to have to do it through the command line.
So it should boot in just a moment, and then we'll get started. I think it's rebooting right after a Windows update, which is probably a small mistake on my part. As we can see, I successfully cloned core on this one instead of using the zip method, created the same build folder, and then all of these solution files is what cmake generated for us, so that we don't have to actually maintain a solution file as well as a series of make files on Unix and an Xcode project file. It's just a meta build system for generating the actual toolchain files that you'll use to compile. So you would just drill into your build folder if you weren't using the cmake UI as I did earlier, and then click on the .sln file on Windows to open it up. And then once that loads, I'm going to demonstrate first how to run the scenario driver. So if you right-click the scenario driver and go to Properties, and then Debugging, there's this field right here, which is command line arguments, and the scenario driver just takes in the path to an XML simulation that's already in runtime or one that you write yourself. By default, the runtime directory will automatically be set to the working directory of the build, so you can do everything relative to that runtime directory once you understand its layout. And that's the same for the test driver or anything that runs inside of here. So then you just click F5 or the local debugger, and the simulation will run. And so here we have all of our physiology simulation running, and we can see the rate at which it goes and whether things stabilize. And we'll run this a little ways to completion, and then I'll demonstrate running the how-tos. The main difference between the scenario driver is just that it can run any simulation, and the how-tos run a specific SDK example. So for them, you can skip the property step, you can right-click and use the Set to Startup project in Visual Studios, and then go directly to running and seeing the results. All of these executables can be installed into one location, and if they are relative to the runtime directory, you could run them just by double-clicking or using outside of Visual Studios to basically just create like a demonstration package for BioGears. I think that's a good demonstration of how that would work. So the one thing I do want to say is that if you were to right-click that directly after building, the window will pop up, but you'll get several push-button notifications that tell you that certain DLLs are missing. And when you get that, or before you get it preferably, make sure that both the scenario driver and the test driver are built, and then just right-click this capital stage target in cmake predefine, and it will automatically scan the EXEs that we built for the required DLLs and migrate them into place that Windows needs it for everything to run. And hopefully that just makes everything simpler for everybody, since Windows as a platform doesn't record the location of its link dependencies at build time.
This is something you wouldn't need to do if you're on a Linux or Mac environment.
Yeah, that's correct. The ELF format for Windows, and I don't know the technical name for the format that OS X uses, but both Linux and OS X record where all the shared libraries were that they were linked against. So if nothing moves on the system, if you're not migrating for like a distributable package, you can simply run them in place. If you move things around, then you would have to set up a search path for them or consolidate them all into one directory the same as Windows. And so this is, we ran the airway obstruction example.
We built it.
Yeah, we built it, you are correct. I skipped my step. So right-click, set a startup project. And then you'll notice the familiar output, and it will run to its conclusion as well.
And the how-tos load in save state patient data that gets copied into your runtime directory. That's why you're not seeing the stabilization step here. If you are running a custom patient XML, you need to go through the stabilization step. And if you would like, you can also create the associated save state for that new patient file. But if you just load a patient file in here, it will go through the stabilization process automatically. We're just telling it that we're loading in a state file.
So I think that brings us to a conclusion of what we wanted to demonstrate today for Windows. I'm going to let this VM run for a little bit longer, and I'm going to start up the Linux VM. We can take any questions while this is going on. And then I'm going to demonstrate a different approach to building BioGears, which is just using the package management system for Ubuntu 18 to install all of the dependencies automatically and stick them into place, and then simply cloning BioGears and starting the build directly without handing cmake any of the configuration or search paths because they're in their default location.
And in a lot of ways, this can be a lot easier to build and a lot quicker to build on a Linux or a Mac environment. There are similar instructions for Mac using the Brew, Homebrew package management system that's similar to the apt-get management system in Ubuntu. So if you're interested in Mac instructions, they should follow fairly similarly to the Ubuntu instructions. If you have additional questions, just reach out to us, and we can help you get set up for that.
So the instructions that we're about to follow, just like we went through, core and then wiki, and then we're going to click on the Ubuntu package management system version. And if you'll bear with me for a minute, I'm just going to assume we're starting from scratch, and we're going to run each one of the dependency installation instructions. And since each one of these installs the binary representation, we get to skip all of the compile time for installing, and so it's much quicker than what we went through on Windows, but it's just a different approach based off of what you're testing.
And using the Ninja build system is also new for our Linux development. So it just allows command line building that's a little bit, basically instead of a make file, we're going to be using a Ninja file. Speeds up the development time, or build time a little bit.
And the dev team gets to say Ninja more often.
Yeah, and it's got an interesting name for a build tool.
So you'll also notice that I'm going ahead and installing the automake install tools because I am going to demonstrate downloading cmake and compiling it because Ubuntu does not use cmake 3.12 as its default. The package management system would install cmake 3.5, which would have worked for the previous release of BioGears, but currently is not enough for some of the newer features of cmake that we're using. Now, we do expect 3.12 to be our stable version going forward. We don't expect to move anything more, but just up to this point, we felt that the features that they had added and the speed optimizations well warranted the requirement. So we've gone ahead and installed Eigen 3, log for CPP5, and Xerxes. So all of the dependencies that we talked, except for XSD, are already installed. And now I'm going to go ahead and kind of buffer all of the commands that are in this into a discussion and let cmake build. So cmake has a few build steps when it builds. It's completely self-contained and only requires GCC. So you run this bash bootstrap command, and I have it hard-coded to use 4 processors, but you can change the parallel flag appropriate to your machine. That's going to build just enough cmake that it can build its own cmake files and create the make system, which will build the graphical GUI that I showed you earlier, the equivalent of that on this machine, along with cmake 3.12. The instructions then repeat in case anything went wrong, how to install Eigen, log for CPP, and Xerxes. So, but as you can see, those commands have already been run. And then the special instructions, thanks to Code Synthesis offering a Debian package of installing that into place. So while that's going on, I'll open up a second terminal, we'll install Code Synthesis, and then we'll start the clone of BioGears core, much like we did on Windows. And as soon as cmake's finished, we'll be able to build and run. Austin mentioned that our commands do use the Ninja generator instead of the traditional GNU make. That is completely optional. You can use any of the generators supported by cmake to build BioGears. Our team has just followed kind of like the open source community and changing preferences for the build speed that comes out of Ninja. So cmake is building. I'm going to go ahead and create a new terminal. And this is the output that's scrolling through of what a GNU make generator would look like. So we'll demonstrate the difference in what the Ninja generation looks like in a second. But let's go ahead and get that XSD installed. So I do end up buffering, yeah, exactly, several commands into multiple copy and paste. Bash is very good about not accepting input after return until the next cn statement, which, if your program doesn't have any prompts, allows you just to wait until the next prompt appears and copy multiple lines in. So our code blocks are made for you to be able to copy and paste them. The problem is that we did not hand the force flag to apt-get, so it was asking yes or no, would you like to install? And that would have then passed these commands if the input's yes or no and caused errors. Just in case. So BioGears is now finished, and we're in the build directory. So as soon as cmake's done, which, as you can tell, is a fairly fast build, we will run the final command to run the configuration step. You'll notice that the only thing that we pass this configuration step is the install prefix, the BioGears build Java tools, and the BioGears build how tools. We don't have to give the cmake prefix path variable that was required. And that is because when you use the package system for all of your dependencies, they're installed into the defaults of user lib or user local lib, and cmake automatically searches those. So it's assumed to be a valid location. And so now that that is done, in the other window that we have open, cmake version 12 is installed. So I'm going to go ahead and run this as a multi-line command. And you'll notice the output is exactly the same. The only difference is what it generated. So instead of generating solution files, it generated a build ninja and rules ninja. And so now we can just type the ninja command, and it will generate runtime as it did. It will then generate all of the CXX and HFX files, and it will begin to build. And once this is done, inside of output/bin would be, depending on whether you're building in debug and release, the scenario driver command or scenario driver _d. So we do tag everything that we build with _d, just so it's very easy to see that that was built with debug, because it's such a performance hit when you use it. I hope this was an informative demonstration of the new build system, and if you have any questions, you can contact Austin or I. Both of us will make our emails and contact information available.
So why don't we throw them up on the screen